Well, over the past 2 decades, America's place as a leader in the global economy has been challenged. Catastrophic events such as the dot-com bubble burst, 9/11, and COVID-19 have showcased the vital role supply chains play in ensuring our nation's security. These events also illuminated the weakness of supply chains while heightening awareness of the need to rebuild American manufacturing. The 2024 NAE annual meeting on reimagining supply chains for national resiliency represents a call to action for the nation's top engineers in business, government, and academia to come together and reimagine next-generation supply chains. This reimagining emphasizes the application of new tools, such as artificial intelligence and human intelligence, to co-create new business models that advance and apply our new understanding of the world's industrial linkages, delivering resilience for decades to come. I'll note that this program was put together by a team of colleagues from your sections and ably co-chaired by A.J. Malshi from Purdue, who's out there somewhere. A.J.? There we go, over in the corner. And we're now off the hook, and this now is on a ballistic trajectory. It goes where it goes. But joining us today is NAE member Laurie Locascio, Undersecretary of Commerce for Standards and Technology and the Director of the National Institutes of Standards and Technology. Laurie will discuss the role NIST plays in empowering innovation for a resilient future. Included in that discussion are efforts to revive America's supply chain, including the effects of the CHIPS and Science Act, which invests nearly $53 billion in funding to bring semiconductor supply chains back to the U.S., create jobs, support American innovation, and protect our national security. Laurie's background includes a 31-year career at NIST, rising from a research biomedical engineer to acting associate director for laboratory programs, the number 2 position at NIST, in which she provided direction and operational guidance for NIST's lab research programs. I did some back-of-the-envelope math. Laurie, I've known you for 2/3 of that time, so anyway, you were 10, I think, when I first met you. Following that, she worked in various leadership positions at the University of Maryland before returning to NIST. Currently, Laurie leads the organization's efforts to bring industry and academia together to enhance economic security and improve our quality of life. Full bios for all event speakers are in your program and on the NAE Annual Meetings webpage. For today's session, we will have 20 to 25 minutes for Laurie's presentation and 15 minutes for questions afterwards, led by moderator Deanne Bell. Now, please join me in welcoming Laurie Locascio to the stage.
Thank you so much, Al, for the introduction, and it is truly a great honor for me to be here today to be part of the celebration for the 60th anniversary of the National Academy of Engineering. I'm excited to share with you today some of the work that NIST is doing right now toward this year's theme of addressing our nation's resiliency and to highlight what we as a nation really must continue to do moving forward. Now, at the time that I was appointed by President Biden to lead NIST, it was very clear that the U.S. was in a fierce international competition around technologies like AI and quantum and biotechnology, which are having and will have significant impact on our economic competitiveness and our national security. The U.S. has a dominant university system and has continued to lead in many of these technology areas and research and innovation that really leads to new emerging tech. We are the inventors, we are the innovators, but unfortunately, we have become complacent as a nation and exposed ourselves to significant vulnerabilities that hinder our ability to fully capture the benefit of technologies invented here. Now, as other countries expanded their manufacturing base and built up highly skilled technical workforces with localized supply chains, we saw the opposite: a steady erosion and decline of the U.S. manufacturing base, and with it, a decline in the U.S. base of highly skilled technical workers. And this is not a new story for many of us in the room. We've witnessed it. We've seen our communities and our families impacted by it. And honestly, we've lauded it in the interest of cost savings, right? So with ready access to just about any product one could imagine, we became lulled into a false sense of security, despite being dependent on highly dispersed and globalized supply chain that is optimized for both profit and efficiency and increasingly vulnerable to disruption. So we saw, of course, all these vulnerabilities exposed by the COVID-19 pandemic with all of its associated economic consequences. So if we think back to a few years ago, we were vaccinated, ready to venture out. Many of us tried to renovate our homes, create new offices and school classrooms in our own homes and movie theaters for growing families. And if you could find a contractor, you may have balked at the higher prices or really lamented the fact that you could no longer get the materials for your renovation, or perhaps you tried to buy a new car or a new appliance, but none were available, of course, because they sat unfinished, waiting for various components. The entire global supply chain had been disrupted by a combination of pandemic-related economic downturns, and add to that natural and man-made disasters that shut down factories, overwhelmed ports around the world, and disrupted global markets, and of course, we all suffered the consequences. And at the heart of so many of these disruptions were semiconductor chips, essential components in virtually every technology and every product, which almost all of our aspects of our lives now depend. Global supplies got lower and lower, as you can see in this graph, spanning 2019 to 2021. And we all felt it really in every aspect of our lives. And many of us asked ourselves, why doesn't America, the place where the semiconductor was invented, have a steady and secure supply of them to power the medical devices we need, to get the appliances and the cars that we want, and to protect our national security? And all of a sudden, everyone in the United States started to think about the semiconductor chip. While the United States led the world for many years in the design and manufacture of these critical devices, our leadership role had languished. In 1990, we made 37% of the world's semiconductors here in America. In 2021, that figure was down to just 12%. And while other countries were investing in their own semiconductor industries to make them, to test them, to package them, the U.S. just was not. And that lack of investment had a notable impact. From 2010 to 2020, in that decade, 122 major fabrication facilities were built around the world. 17 of the 122 were built here in America. Now, addressing this decline and fixing these glaring supply chain vulnerabilities required bold action. And as the U.S. had done at least a few times before, like with the Manhattan Project, the Apollo program, the Human Genome Initiative, we decided to place a big bet on science and technology, but this time to reclaim our position as the global leader in advanced semiconductor electronics through the creation and the passage of the CHIPS and Science Act. Now, make no mistake, the CHIPS and Science Act was a $52 billion big bet on science and technology leadership. This was a pivotal bill, and it provided the Department of Commerce and NIST with $50 billion of that $52 billion, $39 billion to incentivize semiconductor manufacturers and their suppliers to build, expand, and modernize manufacturing facilities here on the ground in the United States. And it provided $11 billion for NIST to invest in a portfolio of R&D programs to create a dynamic new network of innovation for the semiconductor ecosystem in the United States. And with these once-in-a-generation resources, we quickly began to build a plan to rebuild American semiconductor manufacturing capacity. And we began to lay the foundation for an enduring capability to once again be the undisputed innovator and advance this field to protect America's economic and national security. Okay, so first, we had to build the domestic capacity to manufacture chips with that $39 billion. And in an incredibly short time frame, we hired experts from the semiconductor industry, financial services, and so many more to stand up this program and implement it at full speed. We brought in a bit of Wall Street to Washington to help us plan and negotiate a portfolio of large deals with major companies around the globe. And we created a highly iterative application process that enabled our experts to determine how exactly these proposed projects would meet the economic and national security needs of our country, while also ensuring that the projects were financially sound with real customers who were ready to purchase the new chips coming off the manufacturing line. And in just 2 short years, we've successfully executed the largest piece of this program. We've announced $36 billion in proposed direct funding and more than $28 billion in proposed loans. And we're working as fast as we can to finalize these deals. You can see a sampling of some of these negotiated deals on the chart on the map here. The green represents large regional clusters of efforts, and blue individual companies and entities, but really all across the United States. And the scale of our U.S. ecosystem is now unprecedented. The total public and private investment will equal roughly $400 billion between now and the end of the decade, far and away the most investment in new production in the history of the U.S. semiconductor industry. So with our $39 billion invested in manufacturing, we've been able to unleash an enormous amount of private capital, about tenfold the original investment. And we have a diversity of technology we've not had in decades. With Intel and Samsung, Micron, TSMC, and SK Hynix, we now have all 5 global leading-edge manufacturers aggressively expanding on our shores. And no other economy in the world has more than 2 of these within their borders. And we're bringing the world's most advanced technology to the U.S. as well. Intel, TSMC, and Samsung will each produce a variation on their 2-nanometer technology. It's the most advanced technology that's currently on path to commercialization. And Micron will produce the most advanced memory technologies in the world, including the high bandwidth memory chips that are critical for AI. And all of these achievements are dramatically increasing our capacity to make chips here. And we've begun to announce funding for dozens of smaller scale projects to fortify the supply chain so that the chip manufacturers have all the components that they need to produce the critical chips that power our lives. Now, prior to 2022 and the passage of the CHIPS and Science Act, the U.S. produced 0% of the world's most leading-edge chips. But now, after these proposed investments, we've changed the global landscape. And according to a report from the Semiconductor Industry Association, the U.S. is on pace to grow its share of global logic manufacturing by 28% by 2032. These are the chips that we need for critical and emerging technologies, like the chips that power AI. Here in this chart, the gray bars show the semiconductor capacity increase by region in the decade from 2010 to 2022. 2012 to 2022. And you can see China's incredible increase in investment in this period, 365%, while the U.S. was stalled at just 11%. The blue bars show what's coming in the next 10 years. From 2022 to 2032, the U.S. is on track to outpace the world with a projected 203% increase in total semiconductor manufacturing capacity, spurred on by the CHIPS Act. Okay, so as we build our capacity to manufacture, we know we must also refresh and rejuvenate our capability to invent and innovate the next several generations of semiconductor technology by investing, of course, in R&D. Our companies will not survive and thrive in the semiconductor space unless we continue to innovate. And we did not invest all these taxpayer dollars in manufacturing just to have the companies come here, build factories, and then fall behind and go away. So all of us gathered here understand Innovation is essential to protecting technological leadership. It was U.S. innovation that built the industry in the first place decades ago. So along with our semiconductor manufacturing capacity, we must also shore up our research infrastructure in this field. The $11 billion that Congress provided for R&D is a significant federal investment that will provide the capability to position the United States as a global leader for efficiently bringing chips from idea to market. The CHIPS R&D program is investing in 4 different areas, and they're shown here: CHIPS metrology, the National Semiconductor Technology Center, the National Advanced Packaging Manufacturing Program, and Manufacturing USA. And briefly, if I could just go down the line, these 4 research programs address: 1, on the left, how you measure the quality and performance of complex devices; 2, how you build and prototype new research devices; 3, how you assemble these devices into highly integrated packages; and 4, how you efficiently manufacture these devices. And if you put them all together, collectively they provide the research infrastructure that simply does not exist anywhere else in the world today. For example, no country to date has invested at the scale and the scope needed to unlock the enormous potential of digital twin technology for our semiconductor manufacturing industry. Until now, Chips for America will award approximately $285 million to form a Chips Manufacturing USA Institute dedicated to digital twins for semiconductors. Okay, so digital twins, for those of you who don't work with them every day, are virtual mimics of what you see in the real world, like a virtual chip, a virtual manufacturing process, or a virtual factory floor. And because this work exists in the virtual world, digital twins can enable collaborative design and process development by engineers and researchers from across the country or across the world. And they can create new opportunities for participation, they can speed along innovation, and they can reduce the cost of breakthrough research and development and reduce the cost of implementation of a new design directly into a manufacturing line. This investment in digital twin technology will provide a competitive advantage for the U.S. manufacturers, and we're very excited to be announcing the winner of the Manufacturing USA competition very soon. And I know that the U.S. companies are excited about it too. We are also leveraging more than a century of technological expertise at NIST to solve some of industry's most complicated metrology or measurement challenges. In the month after the bill became law, we identified 7 grand challenges, one shown here, that require critical advances in measurement science to achieve the next generation of breakthroughs in semiconductor development and manufacturing. For instance, the industry told us it's getting more and more difficult to measure the quality and functionality of smaller and smaller devices, particularly as single features are at the atomic scale and devices are built in 3D. In the past year, we have funded more than 50 teams on 34 projects with $130 million to address with industry these exceedingly difficult measurement challenges. And we know together that we must develop the tools and the technologies to measure the performance of these extraordinarily intricate devices at speed and at scale in order to keep up with the needs of industry. Now, one of the most important supply chain vulnerabilities being addressed by CHIPS R&D is the domestic deficit in advanced packaging. So let me just talk for a minute about why advanced packaging is both interesting and important. Now, years ago, along with moving our chip manufacturing overseas, we also decided it was more cost-effective, much, much cheaper, to package and assemble devices like these shown here overseas. Since putting chips into packages with an enormous amount of wires and connectors was really a labor-intensive manual process. In fact, we do very little packaging here in the United States. I think it's less than 3%. But companies around the world pretty recently realized that they could start to gain incredible efficiencies and incredible processing speed if if they packaged the devices in a different way. For instance, they could package these devices in 3 dimensions, stacking up the chips with different functionalities like memory and logic and sensors, including chips for communicating, chips for taking images, and chips for processing sound, all of which you need in your phone. And by doing that, by redesigning the 3-dimensional architecture, the devices could be made to be faster and more efficient. And today, we know that advanced packaging could lead to incredible gains in system performance and function. Advanced packaging can enable also reduce physical footprints, lower power consumption, and potentially decrease costs overall. And these are incredibly important technology advances associated with the way that chips are packaged, particularly when you focus on high-performance computing and low-power electronics. Again, those chips that are needed to enable continued progress in AI. So the National Advanced Packaging Manufacturing Program within CHIPS R&D will soon award $300 million in projects for the next generation of materials to support novel advanced packaging. And the program is also set to announce its investment in $1.6 billion additional dollars this fall in an open competition for new advanced packaging R&D activities to establish and really accelerate domestic capability in this space. So we're already anticipating investing $2 billion into advanced packaging research, the science of how you put chips together to make a device. Now, if the U.S. is investing $2 billion, you know that we, the government, the industry, do not consider packaging to be either a boring or a trivial thing. In fact, it needs quite a bit of innovation and discovery and is considered to be on the critical path to higher performing chips. Now, the technical requirements to build the advanced packaging ecosystem in the United States, starting from almost zero, will be challenging. We need new teams that can collaborate across industry, government, academia, because modern engineering, we know, is not a solo sport. This is an incredibly exciting opportunity that will push our industry really further than we've ever gone before, and we want to do that together. And finally, the last critical piece of the efforts to strengthen R&D capabilities in semiconductors and other advanced microelectronic technologies is the National Semiconductor Technology Center, or NSTC. And with the NSTC, we're partnering with a nonprofit called NatCast that will be operating the NSTC on behalf of the government. It's a very unique structure for government, but we've been informed by stakeholders, and we wanted to build something from the ground up that is independently operated and could be sustained for decades to benefit U.S. innovation. Now, last month, with our partner NatCast, we kicked off the process to select 3 Chips for America R&D facilities that will equal billions of dollars of total investment. And the facilities will include a facility for advanced chip design, that first one up there. By the way, chip design is an area where the U.S. still leads the world, and we do not want to lose that capability. A combined chip prototyping and advanced packaging facility, and a extreme UV photolithography center. When fully operational, these 3 state-of-the-art facilities will be world-class destinations for advanced semiconductor R&D in the United States, really a place for the brightest minds to come together and collaborate on the industry's most challenging problems. And we anticipate these to be centers of energy for the U.S. in semiconductor innovation. Now, the NSTC here, it addresses a glaring gap in the current domestic ecosystem, which lacks access to prototyping and testing out new ideas. The goal here is to accelerate the pace of these new innovations, going from idea to marketplace by giving members access to prototyping research facilities, access to partners across the entire ecosystem, access to an investment fund, into research funding, and workforce development funding, because it's critical that we address the U.S. job and skills gap across semiconductor design, manufacturing, and production. So I hope I've convinced you that the work that NIST is doing in chips will help to rebuild our capacity in manufacturing while positioning us to continue to lead in the development of next-generation semiconductor technologies. You know, the CHIPS and Science Act is really focused on ensuring we fix the mistakes that we've made in the last decades, where we lost so much of our ability to make things here, making ourselves shockingly vulnerable as a nation. Now, to continue to be competitive in emerging technologies like AI or quantum or biotechnology, we have to make sure that the same thing does not happen again. And so I'd like to spend a few moments talking about some of the efforts NIST is taking to make sure that is the case, that we don't make these same mistakes again. And I'm going to focus this on quantum. The capabilities stemming from quantum contribute a lot to our everyday lives, and in many more ways than most of us realize. The bulk control of atoms, electrons, and photons has enabled MRIs, semiconductors, the internet, and atomic clocks that are the basis of GPS. NIST's own work in quantum stretches back decades. In fact, we developed the first atomic clocks over 70 years ago. And years of NIST research in the development of and the phenomena of quantum physics have given us the tools to better understand how the universe works and how to control and manipulate matter at the smallest scales and the coldest temperatures. Our research stretching from 1980 to the early 2000s led to 4 Nobel Prizes in quantum science and technology. These were fundamental discoveries that led to the emergence of various approaches to quantum computing and quantum sensing that exist today. NIST quantum research has really revolutionized the development of quantum clocks. We continue to really push forward our quantum clocks, and our development of the most accurate and precise quantum clocks, atomic clocks, will help redefine the second on the global scale in the not-too-distant future. Our current clocks for time standard lose less than 1 second in 300 million years. NIST quantum logic clocks are so precise that they can be used to measure gravity and confirm the most fundamental theories of physics. Researchers at NIST have measured the slower ticking of the clock when it was just 33 centimeters, or 1 foot, if you like that, lower than an atomic clock used as a reference, confirming predictions from Einstein's theory of relativity. However, NIST research has applications far beyond breakthroughs in fundamental physics. These efforts, combined with our capabilities in nanoengineering, have enabled a broader development of quantum devices. For example, NIST researchers have used ultra-cold rubidium atoms to make a gyroscope that is far more sensitive for rotations than traditional designs. And these atomic gyroscopes could potentially be deployed on satellites, airplanes, and ships and help them navigate even when GPS signals are jammed or otherwise unavailable. Okay. But let's go back to the story I was telling at the beginning, the story of inventing something here and making it and manufacturing it somewhere else. What is NIST doing to prevent that from happening in quantum? With the passage of the National Quantum Initiative, NIST established the Quantum Economic Development Consortium, or QEDC, and that's led by SRI. The QEDC, with Celia Merzbacher at the helm, brings together companies and federal labs and academics from across the United States to tackle important pre-competitive challenges needed in the quantum field to move the field forward and help companies enter the emerging quantum market successfully and also get the supplies that they need to manufacture here. So the QEDC looks at issues like supply chain vulnerabilities, as well as the standards that can support the development and sale of quantum technologies across the world. The point is, if we can invent it here, we can help support the environment to make it here. You know, researchers around the world know the United States for being very prolific idea generators. We are known for our innovative ideas, but we're not particularly known globally for building reliably great things. Building reliably great things, that's manufacturing, and we lost a lot of that. And manufacturing, well, that's That's engineering, right? So this is really a call to all the great engineers in the room to help us be known once again as the country who makes great things reliably. Now, to end this story, while I'm tremendously proud of the work that NIST does to help innovation and industrial competitiveness in every sector of the economy, from semiconductors to AI to quantum, NIST and the country are at an inflection point. Across the U.S. and science innovation ecosystem, investment in research and facilities and manufacturing science and in workforce development has not kept pace with national needs and threatens our U.S. leadership. While our strongest global competitors are increasing investment in science and technology, the U.S. is simply not. This graph is taken from a report from a few years ago showing data from 2000 to 2019. It's a report that the Council on Competitiveness put out. But you can see the rapid increase that our strongest competitor has been making in R&D compared to the United States. And last year, there were many cuts in federal S&T budgets, including NIST, who experienced a significant cut in program funding and facilities funding. And almost at exactly the same time, this year, China announced a 10% increase in 2024 in science and technology investment. And honestly, this just makes sense because we know that science and technology investment is how great economies are built, because we've done that. So with so much work to do, NIST and the U.S. federal S&T enterprise cannot go backwards. The federal dollars that fuel research and partnership between federal labs and national labs and academics and industry, they power our great economy, and they feed our superpower, and our superpower is an innovation mindset. So if the U.S. is to continue to grow and thrive in so many areas, we need everyone's voice to ensure the continued support for science and technology, because that is the key to our resilient future. It's time for the United States to make another big bet, a big bet on science and technology, and one that is proactive and one that is forward-looking. So thank you so much for your attention, and I look forward to your questions.
Please join me in welcoming Deanne Bell, TV host and founder and CEO of Future Engineers, who will moderate the Q&A.
All right. Hello, everyone. Thank you so much, Laurie, for all of your remarks and just a fascinating presentation. I know I learned so much about the CHIPS and Science Act and QEDC. At this time, we will open it up for questions. So I want to encourage all of the members that like to ask questions to come to the microphones here in the aisleways here. They're open for questions. But I'll go ahead and kick it off with an opening question. You mentioned a time frame of 2032, looking at goals for increased semiconductor production. Can you talk to me a little bit about sort of those timeframes and what our metrics for success look like?
Yeah, the metrics that we look at really are production. We want to make sure that by 2032, the fabs are built, production is really happening, and we're pushing out chips onto the market. As I said, when we designed this program, we really have tried to make sure that the customers are going to be there, when the chips are coming off the line. So we have really anticipated what's coming when and anticipated the growth in the market and then where the chips would be bought and who would actually be online to purchase them. So it's really been sort of planned in lockstep with really the entire supply chain in mind. And then as far as R&D, we are hoping, we would like in the next few years to have those capabilities and facilities built and designed and people ready to come and participate in R&D with us at those facilities. So yeah, that's the plan.
Wonderful. We will go here for our first question.
Yeah, so I'm wondering how you're going to manage the security and also how you're going to manage the thievery of intellectual property. I mean, it's
Yeah.
going to be really critical to do that if we're going to have leadership. If we don't do that, we don't have leadership. We're just handing off our information.
Yeah, you're absolutely right. We have a lot of guardrails that are built into this program to make sure that we can protect IP that's developed in the R&D, but also in the fabs that are built here in the United States. I can provide links to all the information that we have on research security and also for the the manufacturing facilities, but they're quite involved and quite intense. So we've had a very, very clear eye on security this whole time. Thank you for that question. Appreciate it.
We'll go over here for our next
Bob
question.
Lieberman from Lumoptics. I have a question. It's very important to maintain or reestablish our lead in traditional semiconductor chips, but one place where I think we've been slipping behind is in the optical equivalent, light on chips, photonic integrated circuits and so forth, and I think the perception is Europe is way ahead on that, especially in the manufacturing and packaging side. And it's also an enabling technology for the quantum devices of the future, so I'd like you to maybe comment on what we're doing to reestablish our lead in that area as well.
Yeah, well, we have at least one program that specifically calls out photonics, and we're going to be funding primarily, though, related to photonic connectors, and that's in the advanced packaging area. But as NatCast sort of starts to build its facilities and its research programs, I'm sure we'll see a lot more coming online. But our initial investment in photonics will be through the advanced packaging program, primarily photonic connectors.
Great question. Okay, over here.
Yeah, you mentioned, great presentation. I'm John Cohn from IBM. You mentioned skills gap once, and I noticed, Deanne, you're the CEO of Future Engineers. What are we doing to actually engage students to go into this field? They aren't doing it in the numbers that we need yet.
Right. It's a great question. So we have a number of various lines of effort around trying to fill that skills gap. We have a new Workforce Center of Excellence that we just launched within NatCast or the NSTC program. We know that we'll have about 100 to 200,000. There's a wide range of the workforce that's going to be needed to fill both these R&D facilities and the fabs, but it ranges somewhere between 100 and 200,000 new workers. So we have deliberately built up an investment of about $250 million in a Workforce Center of Excellence. Our initial funding for the Workforce Center of Excellence is really going to be around taking some of the existing best programs that are out there and trying to amplify them and scale those up across the United States. But we have a lot of work to do to try to make sure that we can cover the skills gap.
Hopefully we can help.
We would love that. Yeah, thank you.
Yes, over here.
Thank you. Early in my career, I worked for Bethlehem Steel.
Oh, yeah.
And even as a freshly graduated undergraduate, I recognized that the corporation was not investing in modern steel technology. Now, there may have been other causes, but 2 or 3 decades later, they're out of business. And when I look at the decline in the semiconductor presence of the United States, the chip presence, I see a similar decline. I'm just wondering, what is the root cause of the decline of the U.S. presence in semiconductor manufacturing? And are there lessons learned from the steel industry's history?
Yeah, you know, it's interesting if you look back at when semiconductors started to be built, designed, built, made in the United States. We had this incredible, what I would say, ecosystem where you had the manufacturers working in partnership with the universities, working in partnership with government. And that was really created kind of a virtuous cycle of, creativity, I would say, that led to the next design and the next design and the next design. And because they were so close together, you really saw these innovations very quickly be taken up onto the manufacturing floor. When we as a nation decided it's cheaper to build other places and we lost a lot of manufacturing capacity, we no longer sort of had that really integrated look at how do you get these new ideas to the manufacturer, or even what does the manufacturer need, or what's even possible to manufacture, right? So I sort of think it's that's why the Chips and Science program really focuses on bringing this whole thing together, trying to develop an ecosystem that the companies can feed off of and build with, right? And at the same time, how the people at the universities and other research institutions really understand what's possible in manufacturing.
Great. Okay, we'll move on to a question over here.
Thank you, Julia Phillips. I'm a member of the National Science Board, and one of our foci over the last several years has been talent development, missing millions, getting many more people interested in science, engineering, technology, and also giving them the background so that as they work through the educational system, they are qualified to continue their pursuing careers in that direction. And we're not talking about bachelor's and above necessarily. Most of the ones you need are actually the skilled technical workforce, which is at a lower level. And I'm wondering what is the government writ large doing, what is DOC doing to help make sure that students understand the careers that are available to them and that they have the skills they need to be able to pursue them.
Yeah, I appreciate that question. I will say that we are partnering with NSF in one aspect of our workforce development. We're just launching a new co-investment in workforce development for the semiconductor industry, and we're really happy about that. We've had great partnerships around government, really thinking about how we're going to build up the skills and the skilled technical workforce in CHIPS, and that relationship is not only with NSF but also with DOE and DOD. You're right. So there are going to be a broad range of jobs that are available. Some are not going to require even a bachelor's level, some community college, some probably certificate level programs, all the way up to BS, master's, and PhD. So we are really going to be covering, the need is covering really that whole, I would say, continuum. And one of the things that I mentioned that we launched recently was that we are looking at trying to amplify and promote these places that do have good semiconductor programs right now. But these don't necessarily have to be BS level or master's or PhD. They can also be certificate programs, apprenticeship programs, and other programs that can really start to get people interested in and attracted to the semiconductor workforce, right? When I traveled around the United States a lot, talking to a lot of community colleges, and I find that the community colleges where internships might be available with the semiconductor industry, there are internships that are like 10-day internships that just give people a peek into what life could be like, and that's had a tremendous impact. So I think we need to be very creative about how we expose people to these opportunities, because they'll be good paying jobs.
Yes,
for everyone.
very much so. And I will say the board is also kind of focusing in on community colleges and the role that they play. But another one is high school counselors and making them aware of what the possibilities are. So I'll leave it at that.
Thank you so much. Appreciate it.
Great. Those are great questions.
I'm Wing Chu from, can I go on?
We are actually going out of time. Is it a quick one? I'm going to give it to you if you can give us a quick question.
Yeah, my question would be quick. I'm Wing Chu from Purdue University. I've been there for 7 years. I was 32 years at the University of Illinois. I think the root reason for the difference that we are seeing today is education. To quote you some figures, China has 4 times our population, but they have 10 times as many engineers. And the reason is education. Another reason is cultural. For instance, Taiwan, which is a very small country with about 30 million people, has some of the best high-tech companies in the world. Like NVIDIA is there, Asus is there, TSMC is there. And we tried to move TSMC to Arizona, but we were not very successful. The reason is cultural. Okay, I think we should look at these 2 root reasons as to why we are not competing with the rest of the world. Okay, that's all I have to say. Thank you.
I appreciate the comment. And that is something, we were discussing with educators all over the United States. It's really how to attract people into these areas. If you go to Taiwan, and I have been to Taiwan, it's very interesting how that is just a nationally known destination as far as the students want to have jobs in the semiconductor industry. It's that revered. So, we have to do a lot of work to try to get students attracted to, attracted to making things again, right? Even when I was at the University of Maryland, we saw tremendous, like all universities, we saw tremendous increases in the computer science department and then not as much in the hands-on engineering. And so we have a job to do, and I appreciate the comments. Thank you.